Okay, we are back. We are going to go over this packet called integrals and Riemann sums. And this is a very interesting packet, I think, that addresses in a kind of a theoretical nature the relationship between integrals and Riemann sums. And, well, okay, I'll just leave it at that. Some of these I think we did already. So I'm pretty sure in the video we did 1, 2, and 4. I'm not even sure if that's true. I'm pretty sure that's true. Yeah, that's true. We did 1, 2, and 4. 3 is boring, and 5 maybe don't do it. Well, let's do 5. Let's do. I guess we'll just do them all. Let's just do 3 and 5. What's 3? 3 says, what's the limit as n goes to infinity of 1 over n times 1 over n plus 2 over n plus all the way to 5n over n. Okay, so the first thing to recognize is that this is a limit. And assuming this limit exists, this is going to be a number. And so our question is, what is this number? And the thing is, we could probably do this in a lot of different ways. This problem could be done even if you hardly know any calculus at all, I guess, because you could rewrite this as, well, you could factor an n out from the bottom, and then this just becomes 1 over n squared times 1 plus 2 plus 3 all the way up to 5n. And there's a formula for the sum of the first n integers. It's n plus 1 over 2. So this whole thing would become 1 over n squared times 5n plus 1 over 2. And just doing this in my head, I'm going to tell you that this is 25 halves. The point is, and that's just the right answer. The point is that doing this limit might involve just doing a limit, okay, or might just involve, might not involve integrals at all. In fact, I just did this problem. The answer is 25 halves. But how are we sort of intended to do this problem in a way that promotes kind of understanding? Well, you're supposed to recognize that this is the limit of a Riemann sum. So is this a Riemann sum? Well, it certainly looks like a Riemann sum to me because it appears that this is delta x, and it appears here that we're plugging in a bunch of things. And so I'm adding up sort of a lot of values of functions. And here it appears that the function, there's a lot of different ways, well, there's a couple different ways of thinking about this. But if this is delta x, then, and it's incrementing by 1 over n each time, then it seems that this is just the x function. Okay, so that's why maybe this problem is a little bit boring. If this is just the x function, then what's going on? Well, the first number I'm plugging into this x function is 1 over n. The second number I'm plugging into this function is 2 over n. And of course, what's coming back is a rectangle, and the height of that rectangle is 2 over n. So that's why I plug in 1 over n, I get 1 over n back. I plug in 2 over n, I get 2 over n back, etc., etc. What makes this a little bit interesting is that this pattern, if you assume it continues, 1, 2, 3, 4, all the way up to 5n. So in fact, there are 5n terms which I'm adding here. And that means that I'm going all the way out to 5. And so the last rectangle, the 5nth rectangle, will be this one. And so, after all of this sort of thinking and understanding, I realize that maybe another way to put it is, if you gave me the function f of x equals x and told me to use 5n subintervals and told me to go from 0 to 5, in other words, if you gave me the integral from 0 to 5 of x, this is the answer to this problem, by the way, and said for some weird reason, hey, instead of dividing up into n subintervals of width 5 over n, why don't you instead use 5n subintervals, and that way delta x will just be 1 over n. And if you do that, then it's precisely this Riemann sum that you would end up with. And therefore, what you are supposed to do with all the problems on this page, as we did in the video, is look at this limit by a process of thinking and drawing, recognize that this limit is just the integral from 0 to 5 of x, and then just do it. Well, in this case, this is just half of a 5 by 5 rectangle, and so the answer is really 25 halves. Okay, good. Let's do 5. 5 is kind of a typo, or maybe it's a bad thing. I don't know what to say about it. Let's just do it. The limit then goes to infinity of 1 over n times, and now here's my Riemann sum. It's n over 1 squared plus n over 2 squared plus all the way up to n over n squared. Okay, now if I think of this as my delta x, and then I think of myself as sort of incrementing by 1 over n each time, then this is sort of confusing me a little bit because it's hard to tell what function this is. But that's why this problem is a little tricky. If I rewrite this slightly as, instead of n over 1, if I write it as sort of 1 over n plus 1 over 2 over n, which is, this is of course legitimate, all the way over to all the way up to 1 over n, then I think I understand what's going on, which is that these numbers, which I'm adding up an infinite, which I'm adding up n of, are in fact the values of the 1 over x squared function evaluated at 1 over n, 2 over n, blah, 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 blah. Okay, and so once you see that that's the function under discussion, then we can make a picture. And what does this picture look like? Well, we have this 1 over x squared function. Let's see, well, I guess that's what it looks like, right? That's 1, and then, okay. And so the question is, plug in a bunch of numbers. What's the first number? Maybe I'll just do this, not to scale. I think it will look better. Okay, so not to scale, letting that be 1 all the way over here. That's 1 comma 1. So yeah. So let's see. What's the first number that I'm plugging into the 1 over x squared function? 1 over n. So there's 1 over n. What's the second number that I'm plugging into the 1 over x squared function? 2 over n, and 3 over n, etc. And I stop when I get to n over n, otherwise known as 1. Okay, and once I see what I'm doing, then I see that, okay, this is just going to be this is just going to be the RAM of of the 1 over x squared function. Now, so far, so good. And okay, so my claim is that this limit, this number 5, is in fact equal to the integral from 0 to 1 of 1 over x squared. And putting it a little bit differently, if you gave me the integral from 0 to 1 of 1 over x squared and asked me to evaluate it using a Riemann sum and told me to use n subintervals, then what would I do? I would take the width from 0 to 1. If I was using n subintervals, then delta x would be 1 over n. Then I would use RAM, and then I would eventually I would produce this exact limit. Okay, so so far, this number 5 is no different maybe than every other problem on this packet, on the first page of this packet. But okay, when you go to now do this integral, you suddenly find, wait a second, if you try to do this, you're just going to get some kind of error. And in fact, this has a name, this thing, it's called an improper integral. And you may have found this very confusing, and you should. And it turns out, let me make sure I don't say this wrong. Nope, I'm not wrong. That there is in fact kind of like an infinite amount of area between 0 and 1 over x squared. And this is a subject that you're going to learn more about next year. And so we don't know how to do this integral. If you try to apply the FDC, it doesn't work. And more advanced techniques will reveal that in fact this integral does not exist. So actually, this limit does not exist. Okay, I don't want to spend too much time on that because it's kind of not what we're trying to do right now. Okay, I'm going to erase this. I'm going to move on to the other problems on this packet, but I think the most interesting problems in the remainder of this packet are in fact, there's sort of two more of these coming up. So, okay, let's go. Okay. Yeah. Number 6 says the integral from a to b of some function is a plus 2b. Oh, and by the way, now, okay, so given that, this is just sort of practice with, I guess, integral manipulations. What's the integral from a to b of f plus 5? Okay, this is just kind of boring, right? You split this up into the integral from a to b of f plus the integral from a to b of 5. And this is, because the problem said so, a plus 2b. And this is, by an integral property, just 5 times b minus a. And so you get 7b minus 3 minus 4a. Cha. Okay, how about number 7? Number 7 says, hey, this is actually just like the front page as well, but with a little bit of a twist. Now this is 1 over 50 times root 1/50th plus root 2/50ths plus root 3/50ths all the way to root 50/50ths. Okay, what is this? Well, once again, you're supposed to be so comfortable with the definition of the limit as a definition of the integral as the limit of a Riemann sum that you just see right through this. Now, this is not quite a Riemann sum because we have only 50 subintervals, but you should still be able to see that this is the square root function, and it's the square root function from 0 to 1, but using 50 subintervals. And so what we're doing here is we're using 50 subintervals, and we're taking the integral from 0 to 1, and if that's the case, then delta x is going to be 1 over 50. And so this is what we did maybe on the very first day of this unit on when we did like area. So this would be like 1/50th, and this would be 2/50ths, 3/50ths, all the way up to 1, otherwise known as 50/50ths. And when you plug those numbers into the square root function, this is the function f of x equals root x, then you get these y values. And then, so the first rectangle has area, root 150 times 1 over 50. The second rectangle has area, root 2/50ths times 1 over root 50, and then et cetera, et cetera. And so you're supposed to understand that this is in fact, this entire expression, though quite complicated, is just an approximation of the integral from 0 to 1 of root x, which, by the way, we have seen to be 2/3. So this is going to be roughly 2/3, but it's an approximation of that integral using 50 subintegrals of equal width instead of n subintervals of equal width. Okay, man, I hesitate to, some of these I want to just skip, but okay, I guess we just keep going. So number 8, integral from a to b of f, they tell me is 5, and the integral from a to b of g, they tell me is -1. And now I have to answer these questions. Is f always bigger than g? So sort of Roman numeral 1. Is it the case that f is greater than g for all x on the interval a, b? And I think the answer is no, we don't necessarily know that. Here, just because the integral is larger, does not mean that the function is larger on the entire interval. The converse is true. If f is bigger than g on the entire interval, then the integral of f will be bigger than the integral of g. That was one of the properties that we proved at the beginning of this week. But for example, you might have a situation like, well, okay, I think I even drew a little, yeah. So this could be a and this could be b, and this function might start sort of negative, but then something like that. This might be f. And that looks roughly maybe correct, that that there's some, well, I don't even know, I don't even have a scale here, but it could certainly be that there's some negative area down here and some positive area up here, but overall the integral would be +5. But g might be different. It might also be a mixture of positives and negatives, but now maybe something like that, where now this could be g, where it spent a little bit of time positive and a little bit of time negative, but the overall integral was -1. Anyway, those are certainly possibilities, and so I can't be sure that f is bigger than g everywhere. In fact, the way I've drawn it, it wouldn't be. So this one is a no. Roman numeral 1 is a no. What's Roman numeral 2? Roman numeral 2 says that the integral from a to b of f plus g is 4. Yeah, that's just true. Because you can split this up into 2 integrals. So that one is true. And finally, part 3, Roman numeral 3, says that the integral from a to b of f times g is -5. Yeah, that's just not true at all. Okay. So that would just, this just kind of, so this is also like a no. That's just a completely invented property that's just not true. That the integral of f times g is the integral of f times the integral of g. It makes no sense either geometrically or using intuition or thinking of it in terms of physics. If you just take these two functions and perform a kind of graphical multiplication. Let's see, I've even drawn them, whether on purpose or by accident, such that they seem to be crossing at the exact same spot, perhaps, these f and g functions. So if you perform a graphical multiplication of f and g, then in fact the f times g function would be positive everywhere. And so you're certainly not going to get -5. That's one way of thinking about it. Let's leave it at that. Okay, good. There's one more little tiny thing, which is this number 9. And okay, I think this problem was written like 20 years ago or something. And 20 years ago, if you tried to type the interval from 1 to 500 of 13 to the x minus 11 to the x plus the interval from 2 to to 500 of 11 to the x minus 13 to the x. If you type this into, say, your TI 83 in 1997, this would blow up and you would just get an explosion. And that's because your calculator, at least some technology, is not sophisticated enough to do anything fancy and is simply just grinding out these integrals using basically like a Riemann sum. If you use the math9 function on your graphing calculator and you try to type this in, 13 to the 500 is such a monstrously large number that you'll just get overload error and blah blah blah. I suspect now that if you did this on like a fancy TI-84, it might work. Or if you type this into Wolfram Alpha, they would definitely just give you the right answer. But the point of this problem was supposed to be that if you do a little bit of thinking, you can figure this out. And the little bit of thinking that we should do here is to use obvious integral properties. In particular, the integral from 1 to 500 can be split up into the integral from 1 to 2 of 13 to the x minus 11 to the x dx, plus the integral from 2 to 500 of 13 to the x minus 11 to the x. And now, okay, this is getting a little sloppy, I suppose, because now I'm also supposed to be adding this one. I ran out of board space, I guess. Of course, now these two integrals are going to precisely cancel each other. And so this entire problem just turns into the integral from 1 to 2 of 13 to the x minus 11 to the x. And now you just reach for your calculator or whatever, and your calculator tells you that this is 14.946. Okay. All right. The most interesting problem on this whole packet, I think it's actually extremely interesting, is this number 10. And I think I'm just going to go over the second one because the second one is more interesting, and then I'll just kind of leave the first one to you. This is, for some of you, well, okay, let's just do it. And I think I mentioned at some point, somewhere, that this topic is now on the AP exam, and this is one of the things that people find extremely hard, teachers as well, to teach this. But I think you guys will like this and get it. This is the limit, as n goes to infinity, of the sum from I equals 1 to n of the square root of 1 over n squared times 1 plus 2i over n. Okay, immediately I recognize that I have been given a tiny hoop to jump through because this 1 over x squared can be taken out, and so really this might as well be the limit as n approaches infinity of, I'll even just take it maybe right out of the, well, sure, I can take it right out of the summation as well, and this is the sum from I equals 1 to n of the square root of 1 plus 2i over n. And the directions, I guess, are just do it, right? So basically find the answer to this limit by interpreting this limit as a Riemann sum, and thus the limit of the Riemann sum will be an integral, and then doing the integral. Okay, well, what makes this problem sort of hard is that there are many, many ways to do it. And thus you may be bewildered by a lack of confidence in any one way. And in fact, the answer is that there just are fundamentally different ways to do this problem. And all of them are interesting, and all of them yield the same answer, and we sort of can learn from that experience. Okay, and this is going to go much better live in class, where I can ask different people for their inputs and thoughts. It will also go much better. When I go over this problem, usually I fill up like an entire whiteboard, so I am already feeling that I'm going to be frustrated trying to do this now. But basically what it boils down to is you have to interpret this as a Riemann sum. So you have to decide what's your function. and one answer to what's your function. So here's sort of answer one. Answer number one is that the function is just root x. If you just look at this Riemann sum and just decide that the function is root x, then you are not wrong. And let's now see what that yields. Well, I can draw the root x function, and I will draw it. There it is. Alright, well, what kinds of things am I plugging into the root x function? Well, let's see. Okay, let me draw a line here, and then let me sort of now rewrite this slightly as the limit as n goes to infinity of 1 over n times the sum from I equals 1 to n. But now what I'm going to do is I'm going to sort of explicitly, in a sort of new color or something, like red, I'm going to write what is the input to the square root function. If you think that the function that we're integrating is the square root function, then you think 1 plus 2i over n is like the input, so to speak. And I'll even write this as 1 plus I times 2 over n to suggest that the general term, so to speak, that I'm plugging in is 1 plus I times 2 over n. In other words, when I is 1, which is, after all, the first number of this summation, then what do I get? Well, when I is 1, I get 1 plus 2 over n. So it must be the case that 1 plus 2 over n is the x value that I plug into the square root function first. Okay, great. Chop, chop. Next, what happens when I is 2? When I is 2, I get 1 plus 2 times 2 over n. Okay, so that's 1 plus 2 times 2 over n. And that number gets plugged into the square root function. Good. I think this is what I want to do. Yeah. Okay. Woo! What happens when I is 3? When I is 3, I get 1 plus 3 times 2 over n. So 1 plus 3 times 2 over n is the next number which is getting plugged into the square root function. Okay, and I keep on doing this until I is n. Well, when I is n, then this becomes 1 plus n times 2 over n, and that's just 3. So 1 plus n times 2 over n is also just 3. Okay, and so I'm now getting pretty close to realizing what is going on, which is that I have some function. The function is root x. The area that I seem to be attempting to find is the area from 1 to 3 under this root x function. So I'll now sort of outline this in red or something. That's 1, and that's 3. And how am I finding the area under the square root function from 1 to 3? I am splitting it up into n subintervals. I am using RRAM, so n subintervals. I'm using RRAM, and I'm plugging in the various sample points, and I'm getting the various outputs. Everything appears good until I start to recognize, well, okay, what is delta x? Delta x in this case is 2 over n. It's just certainly true that this width of this interval is 2 from 1 to 3. I'm using n subintervals. I just clearly am adding up n things, so I really am using n subintervals. And the width of each one of these rectangles just is 2 over n. And so, like has come up once before in this class, I am now sort of unable to say that this is quite exactly an integral yet. It's not quite an integral yet because this 1 over n is not the width of a subinterval. In fact, the width of the subinterval is 2 over n. And so what we may do is sort of stick in a 2 and undo the damage with a 1/2. And if I do that now I have that this is now an integral, and specifically it's the integral from 1 to 3 of root x. Okay, and now when we just find the limit, hi Theo, now we just finish this limit by computing this integral, we can just use the FTC, and we get 1/2 times. What's the antiderivative of x to the 1/2? It's 2/3 x to the 3/2 evaluated at 3 and 1. And so we get 1/3 times 3 to the 3/2 minus 1 to the 3/2. What is he doing?
I think he's discovered like new ways to make noise.
Whoa. Okay, 3 to the 3/2 is 3 root 3. So this is a third times 3 root 3. Is this just root 3? Is this just the answer somehow? No, something went wrong. Oh, oops. Because there's still, that is 3 root 3, but then there's still just this minus 1. So, okay, I don't know what you could leave it like that, or if you prefer, you could write it as root 3 minus 1/3. Alright, the answer to this problem is root 3 minus 1/3. And great. Okay, this was answer number 1. Answer number 2, and okay, we just have to squeeze this in, so we're gonna freaking squeeze it in, man. And because I think there are at least 3 ways to do this problem. Probably there's just like 3 ways. Good. Sorry, I forgot what I was doing. Okay, so what's another way to do this same problem? Well, I think it's perfectly legitimate, and I'll sort of now rewrite over here what's going on. This is the limit. As n approaches infinity, we're going back to this step of 1 over n times the sum from I equals 1 to n of. Now, perhaps when you looked at this, perhaps you saw this differently. Perhaps what you saw is the square root of the function to you was the square root of 1 plus 2. No, sorry. Oh man, what am I trying to do? 1 plus. Give me 1 second. I guess the other thing you could do is 1 plus 2x. This would be the other extreme. Maybe I don't need to do 3 answers. Maybe, well, okay. We could do 1, maybe 1 plus x is the better one. Okay.